Hello, this is Stephen Neshiba, and I'm here to help you out with the CGI on the molecular orbitals having to do with NH3, BH3, the Lewis adduct. So here's the deal: you'll build ammonia first, and which I've already done here, the usual way, and here's the molecular orbital diagram. We've got the ground state and so on, and so there we have an orbital. It looks kind of like a bonding orbital there, and as you go up here, that's the next highest one, until we get up to the HOMO. And how do we know that that's the HOMO? Well, because I know NH3 has 8 electrons altogether. That's 5 valence electrons for the nitrogen and 1 for each of the hydrogens, and so on. So when we look at what's called the lone pair of that Lewis base, what we think usually is that that would be the HOMO of the Lewis base, which would be this orbital that we're looking at right here. Now we'll do the same thing for BH3, and there's the ground state MO for BH3, and how many valence electrons does BH3 have? Well, that's 3 for the boron. And then 3 more, so we have for the hydrogen, so we have 6 altogether. And as you can see, therefore, the Spartan is labeled the HOMO correct. That's the next orbital up here. Now, when we're talking about Lewis acid-base reactions, it's the LUMO of the Lewis acid, and that would be that one right there. So here we have the LUMO of the acid, which is supposedly going to merge somehow with the HOMO of the base, and so I'm just going to kind of go back and forth between there. Once again, here is that's the HOMO for the base, and there's the LUMO for the acid. And because those look like they're capable of constructive interference, then perhaps that would form a bonding molecular orbital. Now you've already figured out how to make the adduct in Spartan, so I'm just going to show the molecular orbitals for that one. Here's the ground state of NH3BH3, and if you count up all the electrons, you'll be able to confirm that we have the correct number of electrons in here. And it's not really going to show me the molecular orbitals here for a minute. There we go. So here's various MOs, and the idea here is that you're going to go cruising through here until you find a molecular orbital that kind of looks like the merged version of the two that we were just looking at here, and maybe that's one that would be a good candidate right there. Okay, and then from the energies, you'll be able to put together an MO diagram. Now, one last note on this is that this is the set of molecular orbitals that will go in the middle of your MO diagram, and in general we expect that there would be a bonding and an anti-bonding molecular orbital resulting from the constructive and destructive interference between those two MOs of BH3 and NH3, but unfortunately the Spartan isn't going to give us the anti-bonding orbital that resulted from that. You won't be able to find it, but at least you ought to be able to find the bonding MO. Okay, good.